define continuity sort of, well, in an intuitive fashion first. So we say that some function, y f of x, is continuous at some point A if I can draw the graph of y equal f of x near x equal A without having to lift my pen off of my tablet. So if I can draw this curve without having to lift the pen off of the tablet near x equal A, then f is continuous at A. So a function f is continuous at A if the limit as x approaches A of f of x is A, meaning as you keep getting closer and closer to A, your y values keep getting closer and closer to what you think they should be, f at A. And so whatever the value is of f at A, the x values being closer and closer to A give you y values that are closer and closer to f of A. So this means that A is in the domain of f and that the value of the limit is equal to that value at A, f of A. Well, what happens when a function is not continuous? Well, it could look many different ways. We have names for some particular values of situations where the function is not continuous. So we have names for the following situations: a removable discontinuity, jump discontinuities, and infinite discontinuities. So a removable discontinuity. If I have that my function is not continuous at A, but if I redefine this function at one point, I could make it continuous at A. So if I take this point, this way up here, and just move it down and fill in this new point. So I've taken this point and I bring it down here so that it is now filled in, and I get rid of that previous point here by moving it down, then the function would be continuous. Okay, good. So that's called a removable discontinuity because I can remove this discontinuity by redefining my function at one point to make it continuous. So this occurs when the limit as x approaches A of f of x exists. So if you find that the function is discontinuous at A, yet the limit exists, then we say that this function has a removable discontinuity. Next, let's look at this situation. A jump discontinuity. Well, what's a jump discontinuity? A jump discontinuity is such that, well, you approach A and then all of a sudden you jump up to some other value and then keep continuing on. And so you start out approaching something nicely, you jump up at a to some different value, and then you continue on your merry way. So notice that in this case, there's no way to define a function here at one particular point to make it so that if you fill in, let's say this point here, you can't all of a sudden now draw this as in one stroke because there's a whole bunch of things in the middle that are missing. So there's no way to just fill in one point so that you could draw it without having to lift your pen off the tablet. So, oops. So this occurs when the limit does not exist. The limit as x approaches a of f of x does not exist. Okay, next. An infinite discontinuity. Well, if somehow your function goes off to infinity, then, well, then the limit doesn't exist, so it's not continuous. So this is called a infinite discontinuity. So this is a situation where the limit approaches infinity, and it could be either plus infinity or minus infinity, or it could be where I still call it an infinite discontinuity if the one-sided limits are infinite. And it could either be plus infinity or minus infinity. And it really doesn't matter which way they go. Well, maybe I should just say it this way. It could either equal plus infinity or minus infinity. So in any of these situations, we would call this a infinite discontinuity. So definition. A function f is continuous from the right at a if the right-sided limit as x approaches a of f of x is equal to f at a. Similarly, f is continuous from the left at x equal a if the left-sided limit as x approaches a of f of x is equal to f of a. A function f is continuous on an interval if it is continuous at every number in the interval. If it is defined only on one side of the endpoint of the interval, we understand it's continuous at the endpoints to mean it's continuous from the right or from the left, whichever one was that endpoint. So if somehow this function here, let's say, was defined only, maybe it's only defined here, then, well, let's say here, this is your function, and this is not defined over here, then this is going to be continuous at a because it's continuous, it's only defined to the right of a, and it's continuous from the right. Okay. And so this would be considered as a continuous function. Now, and this is sort of a, well, we'll say that in a second. So it would be continuous on the closed interval. So this would be continuous on the closed interval from a to infinity, assuming that, I got rid of this part here. So let's restate this definition of continuity in terms of epsilons and deltas. So we call a function f is continuous at a if the limit as x approaches a of f of x is f of a. So let's restate this in terms of epsilon and deltas. A function f is continuous at x equal a if for every epsilon greater than 0, there exists a delta greater than 0 such that x minus a in absolute value less than delta implies that f of x minus f of a in absolute value is less than epsilon. Notice in this definition, since previously we didn't care what happened at a, as a matter of fact, we didn't want to know what happened at a, we had to say that x minus a in absolute value was greater than a, was greater than 0, so that x could not equal a. In this case, we want that the function is, that this limit is equal to f of a at a. And so I get rid of that, 0 less than on the left-hand side, so that I have that this works for all x less than delta, for all x that are close to or equal to a. So I want that this works at a also. So a function f is continuous from the right at a if for every epsilon greater than 0, there exists a delta greater than 0 such that x minus a less than delta implies that f of x minus f of a in absolute value is less than epsilon. A function f is continuous from the left at a if for every epsilon greater than 0, there exists a delta greater than 0 such that negative delta is less than x minus a. Implies that f of x minus f of a in absolute value is less than epsilon. Continuous functions. A function f is continuous if it is continuous at every point in its domain. So note the following. So this is sort of a strange, it's an obvious definition, but then when you look at it in pictures, it's not as obvious as it should be. So let's say that this is, that here's my function. This function is continuous, a continuous function, because it's continuous everywhere that it is defined. It's not defined at that open hole. Therefore, it's continuous everywhere that is defined. So this is continuous. Whereas if you happen to have a dot there, this is not continuous. It's not a continuous function. It's not continuous because, well, it is defined at this point, let's say A, but it's not, the limit is not the same as the function, the value of the function at that particular point. So this is not a continuous function. This is a continuous function. So here's another continuous function. Again, because it is continuous everywhere it is defined. So the sort of intuition I gave you before, well, the intuition still works, but it doesn't, the intuition doesn't work when I say continuous function. So a function is continuous if it is continuous everywhere in its domain. So the fact that you have these discontinuities at points that are not in its domain, I don't care. So I'm sort of blind to the fact that there is this discontinuity here at 0, because 0 is not in the domain. I disregard this discontinuity again because it's not in the domain. I do look at this because this is in the domain. It's not continuous here. I only look where the function is defined. If it's continuous, where the function is defined, then it's a continuous function. If it's not continuous, where it's not defined, I don't care. So I don't care that it's not continuous where it was not defined. Okay. So,
Professor, I have a question.
yes.
When you say defined, you mean like in the problem it'll tell us in where? Oh, okay. Okay, I understand that now.
Well, yeah, that would be nice if it always said where it was. So the answer is sometimes. So if you recall, theoretically, when I have a function, I should say it goes from A to B. I should give its rule, and I should give its domain. But most times, I only give the rule. I say let f of x equal x minus 2 over x minus 3. And that's all I write. If you may notice in your book, that's what they do. Let f of x equal x minus 2 over x minus 3. In which case, this is understood to be the natural domain. What is the natural domain? It is the largest possible domain that gives a real valued function. And so in this case, don't divide by 0. It's all numbers except for x equals 0. So the domain is everything except for 3. So you don't want to divide by 0. So if they give you the domain, then it's whatever they state. But 99% of the time, they're not going to give you the domain. So it's the natural domain. Meaning, when, so that gives you back to this other situation that I gave you, which is suppose someone wrote down f of x equal 1 over x. And they wrote that down. This is a continuous function. Why? Because it's understood to have the natural domain, and your natural domain will not include 0. So it never includes the bad points. Is that clear? This is actually very confusing. So this is a confusing terminology because it sort of almost contradicts what I said at the beginning. And that's life. That's so just remember, put on your blinders for values of the function where it's not defined. That will tell you if it's a continuous function or not. And so f of x equaling 1 over x is a continuous function. So now, with this definition, it actually gives you now the nice part, which is basically everything that we look at is a continuous function. So a polynomial function f is continuous at every real number c. A rational function f over g is continuous at every real number except when you divide by 0. So it's continuous at every real number c such that g of c is not 0. Remember, polynomials, the natural domain of a polynomial function is all real numbers, and the natural, which is where it's continuous, the natural domain of a rational function is every real number, except for those where you divide by 0. Therefore, every polynomial function is a continuous function. Every rational number is a continuous function. And so, basically, everything that we look at in this class, except for the counterexamples I give you, well, most of the, so 99% of the problems, examples that they give you in the book are continuous functions. So let's show this. Well, let a be a real number. Then the limit as x approaches a of a polynomial function f of x is just f at a. We showed that in in section 1.7. Next, let a be in the domain of f over g. Then g of a is not 0, because if it were equal to 0, then it would not be in my domain. Therefore, the limit as x approaches a of f of x over g of x is f of a over g of a, from the theorems that we proved back in section 1.7. Here. So now I'm going to give you a function that's not continuous. So now finally I give you, and usually, how can you tell something is not continuous? Usually, well, not always, but at least for most of the examples that we give you, it's a piecewise defined function. So usually what we do is we give several rules, and then that will make our functions not be a continuous function. There are other ways to do it, but 99.99% of our discontinuous functions will be defined as a piecewise defined function. So let f of x equal 1 if x is greater than 0. So let it be 1 if x is greater than 0. Let it be 0 if x is equal to 0. And let it equal -1 if x is less than 0. So this is sometimes called the sign function. It's the SIGN function. It gives you the sign of your number. Well, is this a continuous function? No. This is not a continuous function because it's defined everywhere, but at 0, my function is not continuous. So my function is defined at 0, but it's not continuous at 0. So the limit as x approaches 0 from the right is 1. The limit as x approaches 0 from the left is -1. Since the left and right sided limits are not equal, then the two-sided limit does not exist.
Professor,
Yes.
what if they were like less than, if it were to be less than or equal to, would that be an exception for the signs to also have the equal?
You mean if I put a less than or equal to, if I put less than or equal to here?
Yeah, and greater than or equal at the top.
Oh, it wouldn't be a function. So let me just see if I understand what you're saying. So let f of x equal 1 if x is greater than or equal to 0, -1 if x is less than or equal to 0. Let's say this, okay?
Only one of them, because then it wouldn't be a function, like you said.
Yes, yes. Okay, so that's fine. So yes, I'm sorry. See, that's why I was asking the
No, I said it wrong in the beginning also.
but that's fine. So let's do this. So this, if I look here, my function would be +1. And -1. Still not continuous. Okay. So yes, that's okay. You can do that. But this is also not going to be a continuous function. So nice and fine. Now, since you sort of gave me inspiration, let's look at, let's look at another one. Suppose I have f of x equal to 1 if x is great, if x is greater than 0. Good. And -1 if x is less than 0. This is a continuous function.
I have a question.
Yes.
Is that because like mathematicians can somehow prove that at some point from approaching 0, it swerves and goes to the top to 1 from -1?
No. No, the answer is no. So if you're trying to say that somehow it's called it's continuous because somehow they match up, no. The answer is no. The reason it's continuous is because, again, you put on blinders where it's not defined. So the reason that this is continuous, I call this continuous here, because I don't see this point because that point is not in the domain. Okay. This at x equals 0 is in the domain. So I see it and I see that I can't join them. X equaling 0 still is in the domain and I see that it's not continuous. Therefore, this is not a continuous function. And so this is, so this also is not, not continuous function. Whereas here, this is a continuous function because I have blinders and I don't see the x equals 0. I only see things in the domain. So in the domain, it looks nice and fine. Now, there are other things So this gives me, so this is another. So this is probably what you're thinking, which is the following. If I look here at y equal 1 over x, I say that this is a continuous function because in this case, I can compactify the line. There's something called a compactification. And so what I mean by this is, let's take this line and let's make it into a circle. So if I take this line, I can wrap it around so that it becomes a circle. So, say here's the origin. And then here's the positive. I go this way. Here is the negative, so I go this way. And then all of a sudden, I sort of join up, except there's a little hole there at infinity. Okay, and I could do that with the other one. So I could make this into a sphere with a little hole. Usually I actually have it in the North Pole, where there's a little hole up here. So it turns out that this actually is continuous because you could actually fill in that little, it is continuous everywhere. And it actually does look continuous now on this sort of compactification of the plane. So it actually, so the answer is yes, but this is not an example of the yes. Okay, so the answer is yes, but you're not filling it in, you're joining things together. I don't know if you understand what I just said.
Could you explain,
Pardon?
could you explain compactification again?
Oh, what compactification is? Oh, that's a hard thing. What do I mean by that? So let's take this line, and what I'm going to do is I'm going to curl it up. Okay, and then keep curling it up until it becomes a circle. I'll actually tell you. Let me give you the real details of it, because the real details aren't that difficult. Let's look at this line. And this is the origin. And let's look at a unit circle. Okay. Now, I can take a point, let's do it in red. I can take this point here and go to any other point on the line. And I will, point on the line. Take a line that goes here. Identify this point on the number line with this point on the circle. So I can identify every point on the circle by points on the line. Therefore, I can make this line into this circle, except at the North Pole. And what I do, oh, you broke up. Okay. There was a comment that you sort of broke up. So this turns out to be, now if I fill in that one point, then that makes this line into a closed interval. And so that's called its compactification. I've made it into a closed thing. And that's, so it turns out that I can join these guys
Do you mind
together.
moving your wheel? I'm just trying to get through.
Okay.
Thank you, man. Appreciate it.
Oh, no, okay, here, yeah, sorry.
They need to be
That
some more.
Yeah, let me try to, I'm going to, oops, unmic everyone, except for me. Let me unmic that. Okay. Yeah, I thought it was a comment. So I'll turn off his mic for a second. Okay, so you can.
So like, just to make sure, like you can't,
Yes.
like, you said something about not being able to do something on the top. I couldn't hear you.
Oh, okay. So this guy here, I cannot join these guys.
Okay.
These guys I can't really join together.
I heard that part, but like for the compactification, like when we like match the
Oh,
points, do we
Right,
match up
we
to
can
the
match
top? of the
every
circle?
point. I can match every point on the circle except for the North Pole.
Okay,
So if you notice, I can go out, as you go out further and further, well, this gives you points here, but you can't go all the way to the top.
okay,
Actually, maybe what I'll do is I'll put, I'll start at the top and then see where they intersect. Whatever, you can never, oops.
is the reason for that because it's like a function or like
Because you can never go to infinity.
okay,
Because infinity is not a real number.
yeah,
That-
okay, makes sense.
Right.
Are we going to use this concept more or?
Not at all. This is a concept. It's only because of a concept. There's something that I think you asked. That even though I said no, there is an idea of yes. And this idea of yes will not be until you take what's called advanced calculus. So it will not be used in this course or in the next or in any of the of our nowhere in this book. Okay.
Okay.
So the answer is yes, but it's more advanced. Okay, I'm gonna erase this now. Okay, so
Very interesting.
yeah, so so the answer is so all I will say is that a lot of the questions become yes eventually, but they may be difficult for me to explain why they become yes. Okay, so let's get rid of all that stuff. Okay. So now let me continue with this example. So let f of x equal 1 when x is greater than 0, 0 when x equals 0, and -1 when x is less than 0. So if I look here at the right side of the limit, well, as x go to 0, my right side of the limit approach 1. So the limit as x approaches 0 from the right of f of x is equal to 1. As x approaches 0 from the left, my y values are always equal to -1. So the limit as x approaches 0 from the left of f of x is -1. Since the right and left hand side limits are not equal, then the two-sided limit does not exist. Therefore, this is a jump discontinuity. So this is a jump discontinuity here. If you notice, you jump. So somehow you go from here and you jump up. Okay. And so this is not contingent 0. Since 0 is in the domain of f, this is not a continuous function. Now, this is an example I gave you above. So let's do another example. Let f of x equal 1 if x is greater than 0. Let f of x equal -1 if x is less than 0. Then f is continuous at every point in the domain. Remember, 0 is not in the domain. At every point in the domain, my function is continuous. And so f is a continuous function. So these functions look almost identical. This is not a continuous function because I can't put on my blinders. Because at 0, it is defined and it's not continuous there. This is the continuous function because I put on my blinders and I don't look at points that are not in the domain. I only look at points in the domain. At any point in the domain, my function is continuous. Is that clear? So this function is not continuous on the real line. It is not a continuous function. This function is not continuous on the real line. It is a continuous function. Is that clear? So it's a continuous function because it is continuous everywhere it is defined. It is not continuous at 0, therefore it's not continuous everywhere on the real line. Any questions about that statement? So it's a very subtle statement. So notice, continuous on real line. Not continuous on real line. Not a continuous function. Continuous function. Okay? Any questions about that? So again, when you say just the word continuous at a point or on an interval, then you look everywhere then you look either at that point or on that interval. If you have the word function, then you only look in the domain. So when you attach this word function, this is where you have to put on your blinders, and you only look where your function is defined. Okay. Which means that you can't, you can't have these, point discontinuities. And so, do the following theorem. If f and g are continuous at C, then f plus g is continuous at C. F minus c is continuous at C. F times g is continuous at C. F divided by g is continuous at C, provided that g at C is not 0. And these are really just easy statements once you use that big theorem that we proved in section 1.7 and reproved in section 1.6. So let's try to show that the sum of continuous functions are continuous. So since f and g are continuous at C, then the limit as x approaches C of f of x is f of C. Since g is continuous at C, then the limit as x approaches C of f of x is g of C. So let's look at the sum of continuous functions. So these two functions will be continuous. The sum of these two functions will be continuous at C if the limit as x approaches C of f of x plus g is equal to f of C plus f of g plus g of C. Well, by the big theorem in section 1.7, limit as x approaches C, f plus g at x is, this is just notation, so limit as x approaches C of f plus g at x, since we define these pointwise, This is just f plus g at x is just f of x plus g of x. But by theorem, I think part A in section 1.7 is equal to limit as x approaches c of f of x plus the limit as x approaches c of g of x. But each of these are just equal to f of c and g of c. So this is equal to f at c plus g at c, which is, again, we define addition pointwise for functions, which is equal to f plus g at c. And that's what I wanted to show. So the sum of continuous functions, the sum of functions continuous at c is the sum of functions continuous at c. I said it's the sum of two functions continuous at c is the sum of functions continuous at c, or the same functions continuous at c. The limit as x approaches c of f minus g at x is equal to, again, by pointwise definition of the subtraction of two functions. It's just equal to, well, f of x minus g of x by the theorem in section 1.7. This is equal to the limit as x approaches c of f of x, which is f of c, minus the limit as x approaches c of g of x, which is g of c. And this, using the pointwise definition of the difference of two functions, is equal to f minus g at c. And that's what we wanted to show. C. So each of these are just easy consequences of that big, huge theorem from section 1.7. C. The limit as x approaches c of f times g at x is equal to the limit as x approaches c of f of x times g of x, which by the theorem in section 1.7 is equal to limit as x approaches c of f of x times the limit as x approaches c of g of x, which is equal to f of c times g of c, which by the pointwise definition of product is f times g, all evaluated at c. And that's what we wanted to show. Lastly, g of c not equaling 0 implies that the limit as x approaches c of g of x is not equal to 0. That's by one of the first theorems actually that we proved in section 1.7. And so the limit as x approaches c of f over g at x by the pointwise definition of function of division of two functions is equal to the limit as x approaches c of f of x over g of x, which is equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, which is equal to f of c over g of c, which by the pointwise definition is just f over g at c. And that's what we wanted to show. And so each of these are easy consequences of the of what we proved in section 1.7. Okay, so note. Continuous functions map continuous functions map connected sets to connected sets and compact sets to compact sets. That's actually called the Heine-Borel theorem. Note that on the real line, a compact set is equivalent to a set that's closed and bounded, a closed and bounded interval. So continuous functions map closed and bounded intervals to closed and bounded intervals. Theorem. Limit x approaches c, g of x equals b. And if f is continuous at b, then the limit as x approaches c of f composed with g at x is f of b. So this says that you can bring limits inside of composition, so long as that function on your outside is continuous. If not, then this won't be a true statement. So if limit as x approaches c of g of x is b, and if f is continuous at b, then the limit as x approaches c of f composed with g at x is f at b. So given epsilon greater than 0, since f is continuous at b, there exists a delta 1 greater than 0 such that t minus b in absolute value being less than delta 1 implies that f of t minus f of b in absolute value is less than epsilon. Since the limit as x approaches c of g of x is b, then there exists a delta greater than 0 such that x minus c in absolute value between 0 and delta implies that g of x minus b in absolute value is less than, let's call it delta 1. Thus, f of g of x minus f of b in absolute value is less than epsilon. Therefore, let's just rewrite this in functional notation. F composed with g at x minus f of b in absolute value is less than epsilon. Okay, good. So that's what we wanted to show. Question, when does this theorem hold? So can I make some of these conditions less strict so that I still have this conclusion, but maybe with statements that are not as strict as these statements? And if I make any weaker conditions, will that mean that this will not hold? Okay, so let's see. So when does this theorem hold? Theorem. Suppose the limit as y approaches m of f of y is L, and the limit as x approaches c of g of x is m, then the following are equivalent. This first statement, limit x approaches c, f composed with g at x is equal to L. I want to show that it's equivalent to this second statement. At least one of the following holds. A, f is continuous at m, which is the statement of the previous theorem. Or B, so here's the other statement. There exists delta greater than 0, such that for every x in that satisfy the inequality, x minus c in absolute value between 0 and delta, we have that g of x is not equal to m. So let's try to show that. First, 1 implies 2, and then that 2 implies 1. So let's show that 1, assuming this, I can show this. Well, suppose that neither of these are true. So suppose that neither A nor B holds. Since B does not hold, so this does not hold, then for every delta greater than 0, change that from the opposite of there exist is for all. The opposite of for all is there exist. So then for all epsilon greater than 0, there exists an x in the interval x minus c in absolute value between 0 and delta, such that g of x is equal to m. For such an x, we have that f composed of g at x is equal to f at m. But since A does not hold, then f is not continuous at m. So f at m cannot equal L. Therefore, f composed with g at x is equal to f at m, which is not L. Let delta equal absolute equal f of m minus L in absolute value. Well, this is greater than 0. Well, all absolute values are greater than or equal to 0. And it's not equal to 0 because we're assuming that these are not the same. Since epsilon, which is f of m minus L in absolute value is greater than 0, then there does not exist a delta greater than 0 such that x minus c in absolute value between 0 and delta implies that f composed of g at x minus L in absolute value is less than epsilon. And so the limit as x approaches c, of f composed with g at x is not equal to L. And that's a contradiction. So therefore, one of those must be true. We have that one of these statements here must be true. Because if both of them were false, then we came with a contradiction. Now let's suppose that 2, let's try to prove that 2 implies 1. So let's suppose that one of these, at least one of these holds. If the first one holds, then, well, by the previous theorem, we've shown that this limit is equal, that 1 holds. So let's suppose that B holds. Then there exists a delta 0 greater than 0, such that x minus c in absolute value between 0 and delta 0 implies that g of x is not equal to m. Since the limit as y approaches m of f of y is L, then given epsilon greater than 0, there exists a delta 1 greater than 0, such that y minus m in absolute value between 0 and delta 1 implies that f of y minus L in absolute values less than epsilon. Since the limit as x approaches c of g of x equals m, then there exists a delta 2 greater than 0 such that x minus c in absolute value between 0 and delta 2 implies that g of x minus m in absolute value is less than, let's say, delta 1. So for x in the interval, well, for x in satisfying x minus c in absolute value between 0 and delta 2, we have that g of x minus m in absolute value is less than delta 1, but that implies that f of g of x minus L in absolute value is less than epsilon. And so f composed with g at x minus L in absolute value is less than epsilon. Let delta equal the minimum of delta 1 and delta 2. Of course, each of those are greater than 0, so delta is greater than 0. Then x minus c in absolute value between 0 and delta implies that g of x minus n in absolute values between 0 and delta 1, which implies that f composed with g at x minus L in absolute value is less than epsilon. So I've proven what I wanted to prove. So corollary. If g is continuous at c, and if f is continuous at b equaling g of c, then the limit as x approaches c of f composed with g at x is equal to f composed with g at c. And so it follows that f composed with g is continuous at c. So let's try to prove the first one. Since g is continuous at c, and since b is equal to g of c, then the limit as x approaches c of g of c equaling b implies that the limit as x approaches c of f composed with g at x is equal to f at b, which is equal to f evaluated at g of c, which is just f composed with g at c. Next, I try to show it the other way. Well, the limit as x approaches c of f composed with g at x is just f composed with g at c. And so it's continuous. Okay, so let's do this. So the axiom of choice. Good things and bad things, I guess. Okay, so in general, mathematicians have a love-hate relationship. At least I do, with the axiom of choice. So first off, let me tell you the bad, and this is something that I still am disturbed with. Since the first time I heard it when I was I was in my teens. The first time that I heard it when I was like 12 years old, the Banach-Tarski paradox. So the Banach-Tarski paradox says the following. Take a golf ball. Take an orange. Take an orange. Slice this orange in a finite number of pieces. I think 3 or 7 pieces. Doesn't really matter. Well, with the construction, I think it is 3 pieces. Now, take those pieces that you've just sliced up this orange into and translate them, move them to a different location. So I slice up my orange, and all I'm going to do is translate. I'm only going to move from the kitchen to my bedroom or to the living room to eat, or the dining room. I'm going to move from the kitchen to the dining room to eat my orange. And so when I get to where I want to eat them, I'm going to rearrange these, as I move from one location to the other. I can move them right, left, up, down. I can rotate them. And these slices of my orange. And then I'm going to put them back together. So I take this, move over here, and I'm going to take these pieces and rearrange and put them together, back together again. It turns out that if I start with one orange, slice it into a finite number of pieces, it's either 3 or 7, depending on how you do the construction. Let's say 7 pieces. Then I can do it so that I start with this orange and I can put it so that it is now 2 identical oranges from where I started with. So I start with one orange. I now end up with 2 identical oranges from the one. So somehow I started with one orange and I moved to a different location. There's no longer just one orange, but when I rearrange them, I have 2 oranges. How in the world? So how is that possible? So that's a paradox. In other words, another way of stating this is I start with an orange, I translate it. So I take an orange, I cut it into a finite number of pieces. Here, I don't know how many. So I have to cut it into several pieces. In this case, it'll be a lot of pieces, but it's a finite number of pieces. I then move it. And when I reconstruct it, this orange now has the same volume. It is the same as, so let's say, the sun. So you start out with something, you rearrange it, and now it's the sun or something. So that's a bad paradox. So if you assume that the axiom of choice is true, then this statement follows. And this is why it's called a paradox, because it makes no sense at all. This, I am still disturbed to this day that, because obviously I don't see it in real life. And not only don't I see it in real life, it's hard for me, well, I understand the mathematics of it, but it's hard for me to accept the mathematics of it. That if you do a translation, that all of a sudden when you re-put these back together, that you're able to get something that's from an orange to the sun, and that it has the same volume as an orange over here, same volume as the sun when you translate it and you rearrange them and put them back together again. And that just doesn't seem right to me. So that's why I don't really like the axiom of choice. But this is very contingent on real number, on the fact that this is, well, let's do this, that this is 3-dimensional space, that I'm talking about the real line cross the real line cross the real line. So that I'm talking about real numbers here. It's very contingent on that, because it's the construction of non-measurable sets of these things that are really weird that you can construct with the axiom of choice. And this is even, I don't know, this is also kind of weird. Hausdorff paradox, which more or less doesn't quite follow, but it's in the same vein as Banach-Tarski. It was a few years after Banach-Tarski paradox that Hausdorff found this paradox. So the Hausdorff paradox is as follows. Suppose you start out with a sphere and you take away points from the sphere and you translate those. You can start out with a sphere. Let's say that you start out with an orange. You take away the seeds. Of course, you're taking away a whole bunch of stuff. After you've translated it and sort of put things back together, you get 3 oranges. And so you take away some stuff, and all of a sudden you get more than what you started with. So again, that's a paradox. And again, that's if you assume the accident of choice is true. The good part. So this is why those are why I don't like it. Why do I like it? Every field has a algebraic closure, which means the following. Let's think of it this way. If you look at the real line, if you take any 2 rational numbers, in between any 2 rational numbers is an irrational number. You can fill in the rational numbers so that after you've taken all these irrational numbers, that it becomes such that in between any 2 real numbers is a real number. It is what's called complete. Okay, so that's nice that I can take rational numbers, any field, in fact, and find its algebraic closure. Gödel's completeness theorem just says basically that you can complete the real numbers. So another good thing is that, well, if you assume the accident of choice, you have what's called Dedekind cuts. And you can actually construct real numbers, assuming that you have these Dedekind cuts. So you can construct real numbers if you have the accident of choice. It's very difficult if you don't have the accident of choice. So I don't know if you've ever thought about this, but I don't know if you know the number E, but what's that? This irrational number to an irrational number. How the heck do you even define that? How can you calculate that? Don't know, right? Even this 2 to the pi. How do you define 2 to an irrational number? And so these Dedekind cuts will allow you to construct these real numbers. So it's nice to know. It's nice to be able to actually construct the real line. Otherwise you're in trouble. If you don't assume the accident of choice, it is nearly impossible to construct the real line. Next, every vector space has a basis. And next, the least upper bound axiom, the least upper bound principle. It says that every set in the real line that has a, let's say, upper bound, has a least upper bound. Now, that's not true for things like rational numbers. So let's say that, this is all numbers from 0 to the square root of 2. And let's not fill in this. So let's say that this set here is a set of all rational numbers. So I'm only going to look at rational numbers that are between 0 and the square root of 2. Well, you can take, 12, 50 as being upper bounds. This says that, well, a least upper bound would be, well, what's the least upper bound for this set here? Well, the least upper bound for this set is where you think it should land, or should be. It is here. Unfortunately, if you're only looking at, say, rational numbers, the square root of 2 is not rational. So the rational numbers do not satisfy the least upper bound principle because, well, this set here does not have a upper bound, meaning there's no member of this set here that is equal to the least upper bound. If it were reals, then it does. And that's how, well, that's one of the good things about real numbers is that they satisfy the least upper bound or the greatest lower bound principle. Either, well, they satisfy both. So with that, I will state the intermediate zero theorem, and then next time I will prove it. We only have 6 minutes. So let f be continuous on the closed interval AB. If f of A times f of B is less than 0, then there exists a number C between A and B for which f of C is 0. So let me do some drawings here to show you what this is saying. So okay, so let f here be continuous on the closed interval. So notice that this function here is continuous on the closed interval. There's no jumps or gaps or anything else between A and B. Next, A of A times A of B is less than 0, meaning that at this endpoint, it's negative. At this endpoint, it's positive. Negative times positive is negative. So this is saying that the values at the endpoints have different signs. I can say that in another way, that at one of the endpoints, it's below the x-axis. At the other endpoint, it's above the x-axis. Then there is a C between A and B. And so let's find a C between A and B, such that at F be continuous on the closed interval from A to B. If FA times FB is less than 0, then there is a number C between A and B for which f of C is equal to 0. First, let's suppose that f of A is less than f of B. So suppose FA less than 0, less than FB. The other case is treated in a similar fashion. Just interchange A and B in the argument. Since f at A is less than 0, then by continuity of f, there exists an epsilon greater than A, such that f of x is less than 0 for all x in the half open, half closed interval, where we include A in the interval, but not epsilon. Let C be the least upper bound of the set of all epsilons, such that f of x is less than 0 on the interval, where x is in the half open, half closed interval, A to epsilon, where A is in the interval, but epsilon is not. Then C is less than B, and we cannot have that f of C is greater than 0, for then f would be positive on some interval to the left of C, but to the left of C, f is negative. We cannot have that f of C is less than 0, for then there would be an interval, the half open, half closed interval, A to T, where A is in the interval, but not T, with T greater than C, on which F is less than 0. And this would contradict the definition of C. Therefore, we've constructed C. We have that F of C is 0. Note that it is very important that we have used in this theorem the least upper bound. And so we have used the least upper bound principle, the axiom of choice. And so we've used the fact that the real numbers satisfy the axiom of choice. The intermediate value theorem. If f is continuous on a closed interval AB, if k is any number between f of A and f of B, then there is at least one number C in the closed interval A to B, such that f of C is equal to k. Well, suppose that FA is less than k, which is less than FB. And just like before, the other case is treated in a similar fashion. Just interchange A and B in what we write below. The function g of x equaling f of x minus k is continuous on the closed interval AB. Since g of A is equal to f of A minus k is less than 0, and g of B, which is equal to f of B minus k, is greater than 0, then by the above lemma, there is a number C between A and B for which g of C is equal to 0. And so f of C, which is equal to g of C plus k, is equal to k. And that's what we wanted to show. So all we're doing is just shifting. So we've shown that, that there is some here where it crosses the x-axis. Now, suppose that instead we're seeing that, it crosses some point here. Well, just shift this down so it looks like we can use the above theorem. And that's all we did. Or shift up or down, so that, we can use the above theorem. And so what this says is that, let's say in the morning, it was 70 degrees, and at 4 p.m., it's 100 degrees. Then somewhere in between, I forget, it was 90 degrees. And so if you start at 70 and you end at 100, then somewhere in between, at some time in between, it was 90 degrees. Okay. theorem. If a function f is continuous and has no zeros on an interval, then either f of x is greater than 0 or f of x is less than 0 for every x in the interval. Okay, so if you never cross the x-axis, either you're always positive or you're always negative. Okay, so let's prove this by contradiction. If f of x change sign, say that f of x1 times f of x2 were less than 0 for the sum x1 less than x2 in the interval. Since f is continuous on the closed interval from x1 to x2, then by the intermediate value theorem, I'm just lazy, I wrote IVT to represent the intermediate value theorem. Then by the intermediate value theorem, there exists a C in the closed interval, in the open interval from x1 to x2, such that f of c is equal to 0. And this contradicts the fact that f has no zeros in the interval. Okay, so just note that all of these statements have really, well, the intermediate value theorem, the intermediate zero theorem. By the way, if your function is a polynomial, then where it crosses the x-axis, we'll call that a root of your polynomial. If f is a function, we'll say that that is a zero of your function, or we'll call it an x-intercept. The set of all zeros of your function will be called the kernel of your function. So it turned out that the intermediate zero theorem, and therefore the proof of the intermediate value theorem, which was really dependent on the proof of the lemma, and this theorem here saying that if you don't cross the x-axis, you're always above or below the x-axis, as long as you have continuous functions and it's on a real interval. These are all very dependent on the fact that the real numbers satisfy the axiom of choice. And so these are all very dependent on the axiom of choice. Okay, so let's do some examples. Oh, here it is. On page 92, problem 17 through 22, explain why the function is discontinuous at the given number a. Sketch the graph of the function. Okay, so I want to show that this function here is discontinuous. So recall that a function is continuous at 1 if the limit as x approaches 1 of f of x is equal to f at 1. Okay, so let's try to figure out, well, each of these. So let's figure out f of 1 and the limit. Well, f of 1. when x is 1, y is 1. And so I have here f of 1 is 1. Okay, now I want to determine the limit as x approaches 1 of f of x. So let's try to determine this limit. Well, when x is near 1, but not necessarily equal to 1, I have that y is equal to x squared minus x divided by x squared minus 1. Okay. So this is equal to x squared minus x over x squared minus 1. So we want to find the limit. To find the limit, well, the first thing is for finding limits of rational functions, you just plug in the value 1 and see if that is gives you some number. So you plug in 1 and you get 1 squared, which is 1 minus 1 is 0. You look at the denominator, 1 squared is 1 minus 1 is 0. So 0 over 0, do more work. So I have to do more work here. So let's do the limit as x approaches 1. Factor out an x. What remains is x minus 1. I have a difference of squares, so factor x minus 1, x plus 1. Well, the x minus 1's cancel. So this is equal to the limit as x approaches 1 of x over x plus 1. Now, of course, these two expressions here are equal so long as x is not equal to 1. So they're equal in a deleted neighborhood of 1. So therefore, the limits are equal. As x approaches 1, well, x approaches 1. And as x approaches 1, x plus 1 approaches 2. So this approaches 1 over 2. But I wanted, so I have here a half and a 1. 1 and a half are not the same. And so these are not equal. So even though both sides existed, both the right and left-hand side existed, we don't have that they're equal. And so because of that, this function will not be continuous. So f of x, so limit as x approaches 1 of f of x is not equal to f of 1. So this implies that f is discontinuous at x equals 1. If f is discontinuous at x equals 1, well, what type of discontinuity is it? Since the limit as x approaches 1 of f of x exists, and since f is not continuous at 1, then f has a removable discontinuity at x equals 1. in order for you to have a removable discontinuity at x equal 1, remember, you must have a discontinuity at x equal 1. So the first thing is, well, does it have a discontinuity? Yes. Does the limit exist? Yes. Therefore, it has a removable discontinuity at that particular point. Oh, I guess we also want to graph this function. So let me actually simplify this function first before I actually graph this function. So let's just simplify. Let's simplify f of x. Well, for x not equal to 1, I know that f of x is equal to, well, we did this from before, it's just equal to x over x plus 1. So let me write this as, well, I have an x in the numerator. So let me add, subtract 1. And so if I look at this first part in parentheses, I can just divide. So this is equal to, so y, x plus 1 divided by x plus 1 is just 1, minus 1 over x plus 1. Oh, so now I know how to graph this. Oh, and let's subtract 1 from both sides, actually. So I have y minus 1 equals a negative 1 over x plus 1. So I can actually now make this into a translation and actually a reflection of a very nice, simple power function, 1 over x. So let's translate. Y equaling negative 1 over x by 1 unit to the left. Oh, maybe I'll say it this way. Left 1 and up 1. Then I have, and let's bring the minus on the other side. So let's just bring this minus here to the other side. And so I have negative y equal 1 over x. And so let's reflect y equal 1 over x about the x-axis. Okay, so let me try to sketch a graph of this. Maybe I'll do red first. Let's sketch the graph of 1 over x. The graph of y equaling 1 over x, something like this. And now let's reflect this about the x-axis, in which case, well, maybe I'll do it in blue. This will look something, I just reflect about, well, that has a little corner there, but I reflect about the x-axis. So this is a sketch of y equaling negative 1 over x. And now let's translate up by 1. Oops. So up 1 and to the left 1. Okay. And so let's do that. So I'm going to do up 1 unit and to the left by 1 unit. Okay, so let's say this is 1. Y equal 1 and to the left 1. So let's say this is, so this will be actually x equal -1. And so it should look, and it's the blue. And so it's like this and like this. Let me, actually, so it looks like this and like this. Except for one little detail that I haven't plugged in yet, which is the fact that, well, except when x is equal to 1. When x is equal to 1, my y value is, so it actually has a little hole here at 1, and it's equal to, it jumps up here. Okay, so let's try to sketch this. So let me actually, so this is the graph of y equal f of x. Let me sketch it here without all those other graphs. And so if I do that, it looks something like, oh, and this is y equal 1, x equal -1. So, oops. So it looks something like this and like this. So this is a graph of y equal f of x. So it has this discontinuity, this removable discontinuity at 1. Any questions about this? Actually, maybe I should move these up a little bit. There. Okay, so maybe I'll put a little red line or something so you can, there. So you separate them. Okay, so any questions about that? Okay. Problems 23 through 24. How would you remove the discontinuity of f? In other words, how would you define f at 2 in order to make f continuous at 2? Problem 24. F of x is equal to x cubed minus 8 divided by x squared minus 2. So if you notice here, when you plug in x equal 2, you get 2 cubed, 8 minus 8, 0, over 2 squared, 4 minus 4, which is 0. So how should you redefine this function here so that f would be continuous at 2? Well, first off, let's find the domain. So notice that the domain, or let's just note the domain of f is everything except for plus or minus 2. F of x is equal to x cubed minus 8. Let's factor that. So by using the the difference of cubes formula, the special product formula, I get that this factors into x minus 2 times x squared plus 2x plus 4. And let's factor the denominator. I note that it's a difference of squares. So again, by the special product formula, this factors into x minus 2, x plus 2. And I have that the x minus 2's cancel. So I have the f of x is equal to x squared plus 2x plus 4 over x plus 2. Notice here, when I do this cancellation, I'm changing the domain of my function. I'm actually making it continuous at 2. So I'm actually changing the domain of, I'm changing my rules. So I'm actually changing the rule for the function. I quote unquote simplified it. I'm actually removing the discontinuity by doing that cancellation. And so so if you look here, that this statement is true if x is not equal to, well, 2. So if I let x equal 2, then I will actually have removed my discontinuity. So notice the limit as x approaches 2 of f of x is equal to the limit as x approaches 2 of the above function, which is just 3. 4 plus 4 plus 4 is 12. 2 plus 2 is 4. 12 divided by 4 is 3. So I can redefine f as follows. Maybe I'll call it my new f. So I'll call it capital F. Redefine f of x as x squared plus 2x plus 4 over x plus 2. Those, then I will have that little f of x is equal to capital F of x for all x not equal to 2. Okay. And capital F is continuous. at x equals 2. So I've removed my discontinuity at 2. Now, so I'm done. So that's what they wanted me to, that's how they wanted me to remove the discontinuity at positive 2. I guess I'll ask you, well, I'm able to remove my discontinuity at 2. Can I remove my other discontinuity? So can I remove this discontinuity here at negative 2? So let's see. So this is sort of like a separate question. So can I remove the discontinuity at negative 2? So let's see if I can do that. Well, the limit as x approaches negative 2 of, well, this function here. Well, let's start with my original function. Not that it really matters. So it's x cubed minus 8 over x squared minus 2, which is equal to, well, just like before, I can factor it as x minus 2. Oops. Times x squared plus 2x plus 4 over x minus 2 times x plus 2. Okay, so I can actually cancel here because these are going to be the same in a neighborhood of negative 2. So in a neighborhood of negative 2, these will still be the same. But let's look at this. This is the limit as x approaches negative 2 of x squared plus 2x plus 4 over x plus 2. Now, I have this two-sided limit. If I plug in negative 2, I'm going to get 4 minus 4 plus 4. So I'm going to get a 4 divided by, well, negative 2 plus 2 is 0. So 4 divided by 0, I don't know what's going on there. So let's look at one-sided limits. So if I look at some one-sided limits, maybe I can figure out what's going on. So let's look at the limit as x approaches negative 2. Let's take positive values. Well, as x approaches negative 2, but from the positive side, well, negative 2 squared. So this approaches negative 2 squared, which is 4. 2 times negative 2 is a negative 4. So that gives you 0 plus 4 is 4. Again, as x approaches negative 2, well, I'm going to get 0, but since I'm taking the values of x's that are greater than negative 2, this is going to be a positive number. So positive divided by positive is positive. We know from, I think it was section 1.7, we proved that if I have something that's going to 0 in the denominator, but in the numerator, it's not going to 0. And we have a positive quantity, then this positive quantity approaches positive infinity. Similarly, we have the limit as x approaches -2. Actually, maybe I'll use this other equation. Limit as x approaches -2. From the right is positive infinity. Limit as x approaches -2. From the left, well, the numerator still approaches a positive 4. As x goes to -2, but for x as being less than -2, this is going to be negative. Positive divided by negative is negative. We have something going to 4 divided by something going to 0. So this goes off to negative infinity. These are not equal. So the right and left sided limits are not equal. Therefore, the two-sided limit does not exist. Therefore, f, you cannot remove the discontinuity for f of x when x equals -2. So we were able to remove the discontinuity at +2, but we were not able to remove the discontinuity at -2. Any questions about that? So sometimes you can remove discontinuities, but other times you can't. So sometimes you're able to do it, other times you're not. Any questions on that? Okay. So there it is. Okay, I'll just check reading messages, but it was from before. Okay, so let's do the next problem. Problems 53 through 56. Use the intermediate value theorem to show that there is a root of the given equation in the specified interval. Problem 54. 2 over x equals x minus the square root of x in the open interval 2 to 3. Okay, so first off, even though we're not supposed to say this, we're supposed to say that an x-intercept, a 0 of a function, is called a root only in the case that we have a polynomial. And so this is not a polynomial. So we really shouldn't be calling it a root. But I must say that sometimes I also call them roots when they're not polynomials. So even though we're supposed to only call an x-intercept a root when the function is a polynomial function, sometimes x-intercepts, roots, zeros are just used synonymously. And so it really doesn't matter, quote unquote, if the function is a polynomial or not. If we say to find a root, we know that really what we're saying is to find the zero of the function. So let's find the zero of this function. So first off, let f of x equal x minus the square root of x minus 2 over x. On the closed interval, 2 to 3. So first off, we note that f is continuous. Or then maybe I'll say. Then f is continuous on the closed interval from 2 to 3. Because, well, f is continuous everywhere except when x is 0 or when x is less than 0. So well, x is greater than 0 in the interval from 2 to 3, closed interval from 2 to 3. Therefore, f is continuous everywhere in that closed interval. Note that f of 2 is equal to 2 minus the square root of 2 minus 2 halves. So this is equal to 2 minus 1, which is a 1, minus the square root of 2, which is less than 0. F of 3 is equal to 3 minus the square root of 3 minus 2/3. 2 minus 2/3, 9/3 minus 2/3 is 7/3. Minus the square root of 3. Well, 7/3 is bigger than 2, and the square root of 3 is less than 2. So you have a big number minus a smaller number, and that's greater than 0. So f is continuous on the closed interval 2 to 3, and f of 2 is less than 0. F of 3 is greater than 0. So f at 2 and 3 have differing signs. So f of 2 times f of 3 is less than 0. So then, by the intermediate value theorem, maybe I'll call it the intermediate zero theorem, since that's what we call the lemma. So then by the intermediate zero theorem, there exists at least one C, I'll call it X. There exists some X in the open interval 2, 3, such that f of x is equal to 0. So x minus the square root of x minus 2 over x is equal to 0. For some x in the open interval 2, 3. And so this says that 2 over x is equal to x minus the square root of x for some x in the open interval 2, 3. And that's what you wanted to show. So you're done. Oh, actually, maybe I should have said oops. So I can, so start end. So I started it and I ended it. Any questions about this?